We are jumping straight into the paper Trajectory-Refined Distillation, authored by Li Jiang, Haron Xu, Yixuan Ding, and Amy Zhang. And here is the core insight you need right now.
Let's hear it.
Modern LLM post-training relies heavily on on-policy distillation, or OPD, but OPD is basically crippled by this structural flaw called prefix failure.
Right, the early hallucination problem.
Exactly. When a student model starts down a mathematically or, logically flawed reasoning path, dense per-token supervision just completely breaks down.
It absolutely shatters.
Yeah, it yields a bimodal teacher mixture and these highly fragmented, basically adversarial gradients. So this paper solves that by moving from token-level loss interventions to trajectory-level output corrections.
It is a huge shift.
It really is. By prompting a teacher to refine the student's entire rollout before distillation even happens, Trajectory-Refined Distillation TRD fixes prefix failure directly. It keeps the model within on-policy support while delivering massive, and I mean massive, gains on hard math and code benchmarks like AMO-bench.
Yeah, well, it fundamentally rewrites the optimization target. We are taking the focus entirely away from hacking the loss function at the token level, right? And instead, we are fixing the text trajectory itself before the loss is even calculated.
With that out of the way, welcome to AI Paper Slap. Today's deep dive into the source material is dedicated to keeping you, our fellow AI researchers and ML engineers, completely up to date with the absolute latest research.
Because we know your compute cycles and, well, your time are both extremely valuable. So we skip all the fluff.
The mission for this deep dive is to really tear down the mechanics of token-level KL divergence in standard distillation pipelines.
Yeah, we need to explore why TRD's trajectory-level optimization might just change how you handle post-training for modern architectures, especially if you're working with the paradigms driving models like, Qwen 3 and DeepSeek V4.
So to understand why TRD is even necessary in the first place, we first need to isolate the mathematical breakdown happening in standard OPD and its parameter-sharing cousin on-policy self-distillation, or OPSD.
Right. Let's set the baseline.
In a standard setup, OPD evaluates per-token teacher supervision along the student's own generated rollouts.
Okay, simple enough.
And OPSD is just the setup where the student and teacher are the exact same model, but the teacher branch gets privileged info, like the ground truth answer.
Which sounds foolproof, honestly.
It does. It sounds totally foolproof until the student hallucinates an early reasoning step.
And that hallucination is the catalyst for what the authors formally call prefix failure.
Yes, exactly.
Because, these models generate autoregressively, right? So an early reasoning error that contradicts the reference answer gets permanently baked into the causal mask.
The context window is just poisoned at that point.
Exactly. The student cannot fix it without explicit reflection or backtracking, which it usually isn't trained to do natively anyway.
I like to think of this early prefix failure like a GPS trying to give turn-by-turn directions after a car has already driven off a bridge.
That is a very bleak analogy.
It is, but it fits. It doesn't matter if the GPS says, take the next left in 500 feet. You are currently airborne.
Right.
The entire route is structurally doomed, and the context is fundamentally broken. So when the teacher tries to evaluate this airborne car, the math just goes completely sideways.
It literally splits. Under prefix failure, the teacher's probability distribution becomes a bimodal mixture.
A bimodal mixture. So it's torn between two competing objectives.
Exactly. One mode wants to just continue the wrong prefix to maintain sequence consistency because, language models inherently want to complete a localized pattern.
Sure, they want to make sense of what's already there.
Right. But the other mode knows the final answer is wrong and wants to pivot abruptly to a correction onset token. We're talking about forcing the generation of tokens like wait, or actually, or let me recalculate.
Okay, so you have a teacher model split between playing along with the bad math or screaming, wait.
Yep.
And this bimodal split destroys standard KL divergence approaches.
Let's look at forward KL first, since it's mode covering and weighted by the teacher's distribution, right?
Right. Forward KL tries to capture everything.
So it essentially forces the student onto that out-of-distribution correction mode. The teacher is shouting, wait, but the student has almost zero probability mass there because it genuinely believes this wrong math is correct.
And training just completely destabilizes.
So what about reverse KL?
The alternative is reverse KL, which is mode seeking and weighted by the student's distribution. But that's a trap, too.
Why?
Because the loss is dominated by the student's current beliefs, so the updates concentrate entirely on the wrong continuation region.
Ah, I see.
The student places high mass on continuing the bad math, meaning the network is functionally learning absolutely nothing useful from its mistakes. The recovery tokens, those critical, or actually pivots, are completely ignored.
You'd think you could just hack the loss function to bypass this, though? I mean, previous papers have identified this noisy signal issue.
They have, yeah. They tried applying top K truncation or, clipping the high KL tokens to stabilize training, essentially just filtering out the most adversarial divergence spikes.
Right, trying to smooth it out.
But those token-level loss interventions don't actually fix the poisoned context window, do they?
No. And what's fascinating here is the underlying concept of the fragmented gradient.
The fragmented gradient.
Yeah, those prior fixes, top K, loss clipping, entropy reweighting, are treating a symptom. They leave the failed prefix completely intact in the context window.
They don't touch the airborne car.
Exactly. Even if you deploy a mathematically perfect omniscient teacher, it remains structurally limited by dense per token KL because it evaluates post hoc.
Meaning the evaluation only happens after the student has already dumped the garbage context into the KV cache?
Let's trace the exact sequence of how that breaks the learning signal.
Yeah.
At position T, the teacher sees the failed prefix and recommends a correction token, let's call it Y star sub.
Okay, got it.
The student updates its parameters to favor that correction. But at position T+1, standard dense KL doesn't actually feed the student that corrected token for the next step.
Oh, wow. It feeds the student its own original frozen trajectory instead.
Yes. So the teacher is looking at a prefix that is now one step deeper into the wrong continuation. It's evaluating the bad math plus one more bad token.
So it just gets worse and worse.
And because it's looking at an even worse context, it again recommends that same initial correction onset token. The teacher repeatedly recommends a pivot across deepening wrong continuation contexts.
That sounds incredibly confusing for the model.
It is. The supervision pairs delivered to the student form a fragmented, nonsensical sequence. The context grows along the wrong path, while the target token remains stuck at the start of the correction. The student literally never gets to see the multi-step unfolding of the actual recovery path.
Okay, let's unpack this. If token-level loss hacking is doomed because it leaves the toxic context window intact, then we are looking at the problem from the completely wrong end.
We really are.
We can't fix the loss function. We have to fix the text being fed into the loss function before we even compute the gradients. Intervening at the generation stage itself seems like the only way out.
The pipeline for TRD accomplishes exactly that, and it's incredibly elegant.
It's 3 steps, right?
Right. It operates in 3 distinct steps. Step 1, you sample a raw on-policy rollout from the student. We call this Y sub O.
And that contains all the errors.
Yeah, it contains all the natural reasoning, including the dead ends and the prefix failures. Then step 2, you prompt the teacher model to produce a refined version of that rollout, which we call Y sub R.
Okay.
This refinement is explicitly guided by the reference solution, Y star. Finally, step 3, you use that refined trajectory, Y sub R, for standard distillation.
The secret sauce there has to be the on-policy support. I mean, when they prompt the teacher to generate Y sub R, they are conditioning that refinement on the student's initial raw rollout, Y sub O. They are explicitly telling the teacher, fix this specific logic. That anchors the new trajectory to reasoning patterns the student model has already demonstrated it can actually use.
Is vital.
It prevents the teacher from throwing out alien, unlearnable solutions that the student's latent space just doesn't have the weights to support yet.
That constraint makes or breaks the entire framework. If the teacher just spits out a brilliant zero-shot derivation that relies on advanced theorems the student hasn't learned, the KL divergence will trigger the exact same instability we saw with forward KL.
Because the student can't mimic a leap of logic it fundamentally doesn't understand.
Right. By conditioning on Y sub O, the teacher effectively acts as an editor, bridging the gap between the student's current capability and the correct answer.
This mechanism is how TRD recovers what the authors call the ideal gradient, or G ideal.
Yes.
Because the loss is now computed over Y sub R instead of the frozen Y sub O, the context correctly grows along the correction path.
It follows the new route.
Right. At position T+1, the student isn't looking at its own hallucination anymore. It's looking at the first token of the correction, and the teacher is supervising the second token of the correction.
It allows the dense per-token supervision to provide a clean, step-by-step learning signal. The context window is actually useful again. Prior approaches treated the exploding or vanishing gradients at the token level, whereas TRD mitigates prefix failure at its absolute source.
Theory is fantastic, but if you're managing a training run and listening to this deep dive, you care about the empirical validation.
Tell me the numbers.
Exactly. How does TRD actually perform when scaled up on rigorous math and coding evaluations?
The experimental setup the authors ran is quite robust. They tested the framework using the Qwen3 model family, specifically the 1.7b, 4b instruct, and 8b models.
Heavy hitters for their size.
Very much so. They evaluated on a heavy suite of competition math benchmarks, including AIM 2024 and 2025, HMMT, Beyond AIM, and AmmoBench. For the OPD setting, they also evaluated code generation on Human Evil plus MBP plus ANAVIM and LiveCodeBench.
The numbers on AmmoBench are the ones that really demand attention. I mean, AmmoBench is arguably the most punishing math benchmark in their suite.
It's brutal.
TRD delivers a roughly 50% relative pass at 16 improvement for the Qwen3 8B model under the OPSD setup.
50%.
Yeah, it took the base model from a 41% pass at 16 up to 61.5%. And it consistently outperformed all the token level baselines, whether that was
That is a massive leap in reasoning capability without scaling up model parameters.
huge.
And what's particularly revealing is the dynamic between the OPD and OPSD setups. In Table 5 of the paper, they compare the two approaches directly on the 4B instruct model.
Okay, let's look at that.
For OPD, they used a separate, larger 8B model as the teacher. For OPSD, the 4B model taught itself.
And I had to read that table twice. The OPSD setup, the 4B model teaching itself, generally produced stronger pass at 16 results across the competition math benchmarks than the OPD setup using the fundamentally smarter 8B teacher model.
Yeah, it's wild.
That feels incredibly counterintuitive. Why would a smaller model, self-correcting, outperform a larger, more capable teacher model, giving it direct feedback?
Well, it contradicts our standard intuition about distillation until you factor in the mismatch problem we touched on earlier.
The alien solutions.
Exactly. A larger 8B teacher naturally refines a problem using logic, syntax, and structural jumps that might be totally beyond the 40 students' capacity to absorb.
Even if you condition on the student's initial rollout.
Even then, the 8B model might introduce phrasing or intermediate steps that pull the refined trajectory completely out of the students on policy support.
Right, so even if the math is correct, the 4B model spends all its gradient updates just trying to map its latent space to the alien vocabulary of the 8B model, rather than learning the core reasoning steps.
It's wasting compute on translation, basically.
But wait, how does the 4B model suddenly generate a brilliant correction when it just failed the problem moments earlier?
That is the magic of privileged context during the refinement phase. In OPSD, the prompt fed to the 4B model during Step 2 includes the ground truth final answer.
Ah, the answer key.
Yeah. The prompt essentially says, here is the problem. Here is your flawed attempt. Here's the final correct answer. Now, map a path from your attempt to this final answer.
Oh, wow.
Working backward from the known target allows the model to map a successful trajectory.
And because it's generating that path using its own weights, the vocabulary, the phrasing, and the cadence of the reasoning remain 100% native to the student.
It's perfectly native.
The 4B model physically cannot generate a refinement that the 4B model cannot understand. It's the ultimate guarantee of on-policy constraints.
The self-refinement acts as a perfectly calibrated bridge. It leverages the ground truth to enforce correctness, but relies entirely on the student's internal logic structures to actually get there.
I'd expect a rewritten trajectory to just be a cleaner version of the same length. But the data shows something completely different when we look at trajectory compression. Here's where it gets really interesting. TRD causes an absolute collapse in the length of the reasoning trajectories.
The scale of the compression is striking. On the Qwen3 8B model, the median token length for the raw rollouts, Y sub O, was around 7.7K tokens.
Okay, almost 8,000 tokens.
After refinement into Y sub R, that median length plummeted to 0.88K tokens.
Wait, what?
Yeah, we were talking about a roughly 9x reduction in token length.
Going from 7.7K tokens down to 800 tokens is a massive drop. Are we sure we aren't just losing critical step-by-step reasoning? How does the model not hallucinate if it skips that much scratch pad space?
Because standard OPD models often suffer from severe length inflation. They haven't actually learned efficient reasoning. They've learned that if they ramble endlessly, spewing out thousands of tokens of redundant calculations, they might eventually stumble into a correct derivation by sheer volume.
So they just brute force it by talking a lot.
Basically, the TRD refinement strips away the rambling. It keeps the critical chain of thought steps, but drops the meandering dead ends.
And this compression isn't just happening on the rollouts where the student originally failed, right?
Yep.
They found this 9x drop happened even on questions the student already solved correctly in the raw rollout. By applying TRD, you expose the model to alternative, much tighter derivations of the correct answer.
This provides a tremendous exploration benefit. The student learns the most direct, elegant path to the solution, guided by the reference target. It disciplines the model to be concise.
But surely, if the student already got the answer right natively, you wouldn't waste compute training on that trajectory, right? Wouldn't you just filter the data set to only train on the rollouts where the student originally failed and needed the correction?
You would think so, but their ablation studies proved otherwise.
Really?
Yeah. They filtered the training data to only include failed rollouts and then ran a separate test only including successful rollouts. In both cases, the pass at 16 performance dropped.
It dropped.
Yeah. You absolutely need the full corpus, both the failed and the successful initial rollouts, to get the optimal coverage.
Why is that? What's the mechanism there?
Because the two subsets teach entirely different skills. The originally failed rollouts teach the model how to pivot and recover from dead ends. The originally successful rollouts teach the model how to compress and optimize its correct reasoning.
Oh, that makes a lot of sense.
If you remove the successes, the model loses the gradient signal for efficiency.
Now I want to challenge the compute trade-off here. Generating Y sub R means you have to run an entirely extra sampling phase before you even start the distillation training.
It does.
You are prompting the model to rewrite its own output, often across massive data sets. For anyone managing a finite compute budget, injecting an entire secondary generation step sounds incredibly expensive.
It is a significant upfront cost. But you have to factor in the downstream savings of that 9x compression. Because those refined trajectories are so much shorter, the actual distillation training phase, the dense KL divergence computation over the sequences, is massively accelerated.
Let's look at the actual wall clock numbers they reported. The paper notes that on Quinn38b, the total time for the entire TRD pipeline was 9 hours and 20 minutes.
Right.
The vanilla OPSD pipeline, which skips the refinement step but trains on those massive 7.7K token raw rollouts, took 9 hours and 40 minutes.
If we connect this to the bigger picture, it means the extra sampling step pays for itself and then some. You're actually saving 20 minutes of total training time while getting a 50% relative boost in accuracy.
That is ridiculous.
And the benefits compound during deployment. You get significantly faster, cheaper inference because the deployed model stops rambling.
It's an operational win-win, but to be thorough, we have to look at the one area where TRD struggled, the live code bench exception.
Yeah, we have to mention that.
While TRD showed incredible gains on math and basic code generation like human evil plus BIC, it failed to match the base model on live code bench, which is a highly competitive, complex programming benchmark. If TRD is so effective at correcting logic, why did it break down on code?
This highlights a critical difference between natural language reasoning and code generation. Live code bench requires highly intricate, interwoven logic structures that map to strict, abstract syntax trees, or ASTs.
And code is notoriously brittle.
Incredibly brittle. When you ask a current teacher model to refine a flawed block of complex code, it often breaks the underlying AST entirely.
Because changing one variable name or, one loop structure can cause a cascading syntax error across the whole script.
Exactly. Math reasoning in natural language has semantic flexibility. You can phrase a derivation differently and still arrive at the correct integer.
Right.
But in complex code, the teacher model might try to introduce an elegant list comprehension to replace a messy for loop, but in doing so, it violates a student's on-policy support or just breaks a dependency.
Yeah.
It suggests that current models simply aren't quite good enough at acting as structural code editors yet without destabilizing the student's logic.
Editing complex code-based architectures is hard enough for senior human engineers. So it's not shocking that current models struggle to preserve the AST while rewriting.
Not shocking at all.
So what does this all mean for you, the practitioner? Whether you're training a custom model for enterprise deployment or pushing frontier research, moving from token-level loss hacking to trajectory-level correction is a major paradigm shift.
Huge shift.
If you are building post-training pipelines, relying on dense, per token KL divergence on raw rollouts is leaving performance on the table, and it's burning your compute budget on length inflation. Utilizing OPSD with TRD can fundamentally improve both your training efficiency and your inference costs by teaching models to find the elegant, short path to the answer.
It completely redefines the economics of reasoning and post-training alignment. Raises an important question, though, something for you to consider as you design your next pipeline.
What's that?
Well, if a 4B parameter model can fundamentally rewrite its own reasoning paths to be 9x shorter and vastly more accurate, just by being shown the final answer as privileged context, are we approaching a ceiling on how much external, human-generated reasoning data we actually need?
That's a profound thought.
Or will these self-refining models eventually hit a wall where they can compress existing logic beautifully, but can no longer invent entirely new mathematical frameworks without an outside teacher?
That is the frontier we are all pushing toward, and maybe the diagnostic landscape of model training isn't quite as murky as it used to be. By fixing the trajectory, we're finally getting a clear, interpretable X-ray of where the reasoning actually breaks down. Thank you for tuning in to AI Paper Slop. We will see you next time.